Hello and welcome back to module number 7. I hope that the assignment with R was easy. I lay out for you what is it entail and how to calculate that. I hope it makes sense. Again, I did not hear any feedback, so if you ran into problems, please let me know. So today's module, what I'm going to talk about in module number 7, I'm going to talk about two subjects: confidence interval estimation and introduction to hypothesis testing. I'm going to cover it quite fast, and I'm not going to stop on the way because I want you to go over that, ask yourself questions if you do not understand, and make sure that it is synchronized to what I cover in the textbook and what I cover in the notes, and make sure that you can actually do that in R just to verify that everything is synchronized and make more sense. So in confidence interval, I'm going to talk about two parts. I'm going to talk about the interpretation confidence. How do we estimate the mean, which is big proportion of it, and then I'm going to talk about how to determine the sample size as a necessary development in the confidence interval for the mean or the proportion. Just again a little bit about some terminology that I'm going to use. I will try my best to repeat that, so you will have some terminology that you'll be able to talk or to understand. So confidence interval for the population, the mean is also the Greek word mu, and when the population standard deviation is sigma, and we have two proportion to it, when it is known and unknown, and I will talk about that too, and when we have confidence interval for the population proportion, we talk about pi. And we have to also remind ourselves that we have a procedure that require us a sample size. So let's start with a point. One of the biggest mistake, and I can admit it for myself, is a point estimate, and it took me a long time to understand that it is a single number. And the confidence interval provides additional information about the estimate. So we have in hand here the lower confidence limit and the upper confidence limit, but we have one point of estimate, and that's where we need to show and to display that in order for us to be more transparent with regard to our result. So in point estimate, we can talk about population, the entire population, or we can talk about a sample. When we talk about a sample, and I want you to remember that I will repeat it again, the entire module in this case is going to be x hat. And when we talk about proportion, in the sample, I'm going to talk about p. So how much uncertainty is associated with a point of estimate of the population? We also need to know that interval estimate provides more information about the population characteristics that does a point estimate. So that's why we need to be more transparent. Such interval estimates called confidence interval. One of the foundation on confidence interval is it cannot be 100%. It can be 95%, it can be 99%, but it cannot be 100%. And so based on observation from one sample, and that's how we apply to it. An example, population has a mu of 368 and have a standard deviation of 15, and if the sample take size 25, we know that by applying the following formula, 368 plus minus 1.996 multiplied by 15 divided by square root of 25 will give us 95%, which means that we are on the realm of the right thing to do to give the result in order for us to do that. So the problem begins when you do not know the mu, the standard deviation. You use the x hat to estimate the mu. So in this case, we need to be very transparent with our procedure. So a sample, when do we do and when to apply, upper level, lower level, contain mu, yes or no, and how to apply that. And again, I am going to use in this module a lot of text description in order for me to make sure that you understand the idea of 95% confidence in order for us to estimate. So 95% confidence is based on the fact that the z-score, it will be equal to 1.96, and again, that's a good way for us to measure that. So the estimate process starts with population, but it also when we are doing a sample random. So the objective is that we will say quite confident that we are 95% confident that the mu is between 40 to 60, and compare it to the entire population, and where in this case we are trying to match up to that. We are going to see that quite often in the news, quite often very soon, when they're going to do a report on the population point of view about impeachment, who is your favorite candidate to become a president. They're going to do estimation based on a sample that is x hat. Back to our idea of the estimate point. The estimate point formula is usually equal plus minus critical value and standard error. Point estimate, as I said, is the idea of where we're starting, or it's a numerical value that we are trying to do. Critical value is where we need to be more transparent with regard to the result, where it'll help us to estimate the point estimate. And we also need to report on standard error, which is the standard deviation of the point estimate. So the level of confidence will contain the unknown. The percentage is less than 100. And again, suppose confidence level is 95%, also known as 0.95. A relative frequency interpretation, again, I'm putting words here to make sure that you understand that it is 95% of all confidence interval can be constructed, will contain the unknown true population. And a specific interval either will contain or will not contain true distribution. So you probably involved in specific interval. So in this case, the confidence interval can be divided into two parts: the population mean and the population proportion. In population mean, we have when the mu is known and unknown. We will look at that when it's known. And in this case, we are using the formula with the x hat, which is the point of estimate. And it's not the sample proportion, but it is the estimate of the point estimate when it's known. And so in this case, we are breaking down the population standard deviation. The population is normally distributed, and if the population is not normally distributed, we will use a larger sample. Finding the critical value, and again, this is where we are applying the z-score in order for us to do that. And I lay out for you where is the z scores come into play, whereas the lower confidence limited and whereas the upper confidence limited is located, and how we apply to it. And we usually have a table that we will show in this case, confidence level, confidence coefficient, and the z-value in order for us to make sure that we are synchronized with that value. The interval and the level of confidence, again with the sample distribution of the mean, is this where we are trying to match the scores with the distribution and match it in order for us to understand. Example, we are taking 11 circles from a large normal population with a mean resistance of 2.2. We know from past testing that the population standard deviation is 0.35. So they're giving us all the information in order for us to determine that if 95 confidence interval from the true mean resistance of the population, and in this case we can determine where is the lower and upper distribution, the range between, and in this case it's range between 1.9932 and the higher case is 2.4068, and this is how I calculate that. The interpretation, again, how do we phrase it, how do we justify it, and I want you to make sure that you understand that, because the next we are talking about is when the mu is unknown. And when it is, do you really truly know when the mu is known? And the answer is probably never. And virtually all real world business situation, it is unknown. So if there is a situation where it's known, then the mu is also known, and so we are able to calculate. But you need to remember that it is often used when it's unknown. If you truly know the value, you need to get a better sample, and that's a general rule that is always applied to. So we talked about population mean when it's known and unknown. Now we need to talk about population proportion. And so in this case, we are going to talk about interval estimate of the population proportion, which is the pi, which can be calculated by adding allowance for uncertainty of the population, p. And in this case, this is the formula that we are applying. And we are looking at the distribution formula for when we have a normal, if a sample size is larger with a standard deviation, we will estimate with the sample data the following. So we have two formula here that we apply to in order for us to do that. So the confidence interval endpoints is where the upper and lower confidence limits for the population proportions are calculated within this formula. P plus minus Z multiplied by Q divided by 2, square root of P, 1 minus P divided by N, and again the P is the sample proportion, the N is the sample size, and it must be NP bigger than 5, and N multiplied by 1 minus P is smaller than 5. Those are the way to do that. How do we write it? How do we phrase it in a paper when your example interview asks you about that? So a random sample of 100 people show that 25 people, and this is an example that I want you to see, and I want you to look at what I phrase and how I phrase it. So the sample of 100 shows that 25 people are left-handed, including myself. From 95% confidence interval from true proportion of left-handers. So the sample, a random sample of 100 people show that 25 are left-handed from a 95% confidence interval for the proportion for the left-handers, and we will apply P plus minus Z multiplied by the P in order for us to show the mu, in this case 0.165, to the upper case 0.334, 0.49, and the interpretation. This is where we come and provide interpretation to our result in order for us to verify, in order for us to make sure that we are openly giving the information that is required for us to make those decisions. And this is part of today's science, open platform to our result. But we did not discuss yet the determination of sample size. And we have the idea of determining the sample size for the mean or for the proportion. When we have one of the things that we often encounter in sample mean and proportion is the margin of error, or E, when we have a specific level of confidence in that equation. So the margin of error is also called sample error, and it can be provided the amount of imprecision in the estimate of the population, or the amount to add or subtract to the point of estimate to the confidence of level. So how do we determine the sample size? We are determining for the mean, and we are also determining the sample error, margin of error in that equation. So the sample error for the mean, and how now to resolve to the n, to get the n formula, and we are determining it by the size of the mean. We must know that the level of confidence we need, which determines the critical value, and again what we talked previously, and the accepted sample error, which is the E, and the standard deviation. Those are the four components that we need to determine and to have it on the paper in order for us to make sure that we are correct and we are transparent in our result. So in this case, let's take an example. We have a sample of 45. What size of sample size is needed to estimate with a mean of plus 5 within plus or minus 5 with 90% confidence? So we plug it into our formula, and we are going to have 1.645 square root multiplied by 45 square root divided by 5 square root, and 1.65 is the 90%, 45 is what we got from the mu, and divided by 5 is with a mean of plus minus. I will add it or multiply it by square, so it will give me 219. I always remind you, always round it up. You are not going to give the population size by that point. We're not going to say, oh, you need to do 219. You always round it up in order for it to make more understandable to the general public. So what about the unknown? Can be estimated with the requirements sample size. And so the issue is we select a pilot sample and estimate with the sample standard deviation in order from the mu to estimate the standard deviation S. So in this case, we are determining the sample size, we are determining the proportion in order for us to apply this formula, the n divided equal to z square, and the value of the mu multiplied by 1 minus mu divided by e square, and that's part of our equation to determine the sample size. And again, I'm going to repeat it a few times in the following slide. I want you to have a procedure how to apply to it, and the pi can be estimated with a plot sample if necessary, and usually we use 0.5 as an estimate of the pi. So this is part of the standard that we often apply. So how large a sample would be necessary to estimate a true proportion defective in a large population? Within plus or minus 3% with 95% confidence. Assume that the sample holds a p of equal 0.12. So the solution in this case is, again, 95%, and we are using the z-score is equal to 1.96, and the error is 0.03, and the p is 0.12. We use it to estimate the pi, and in this case we use the n 451 as the required sample size. The confidence interval for population total example, another example, again a firm of a population of 1,000 accounts wishes to estimate the total population value. The sample of 80 accounts is selected with the average balance of $87.6 and a standard deviation of 22.3. Find the 95% confidence interval of the total balance, and this is the procedure that I take in order for me to verify if I am on the right track, and it is between 82 to 92. How do we apply that into R? And this is a good question, and I want you to have a good sense of it. The mean with the standard deviation in R is called the function called Q norm. And the mean for standard deviation using the summary statistics in R is Qt. And the mean with a standard deviation for unknown in R is a little bit more complex. It's called t-test, and we will talk about t-test in the upcoming module. But for now, we will assume that the t-test is the way for us to find the standard deviation for unknown sample. The proportion using statistic in R is Q norm. So let's take an example. We have a container with a sample size. Estimate the mean salary for all recently graduate students. Find 90% and 95% confidence interval from the mean, and the answer is, I copy it from my textbook. I do apologize, I'm lazy sometimes, but this is how I do that. So again, what we have is here is a formula, x bar, and we have that, and what we have is the idea of the mean x. It will give us, and then I will take it to the next level. I will call it me, and I will say what is the result of 1.66 multiplied by 50,000 square divided by square of 10, and it will be the equal me, and the lower and the upper boundaries will be calculated based on x, and it will give me the score result. I hope the scale or this illustration of the code is correct and makes sense to you, because I try to catch it so you will be able to see it in face-to-face, download the paperwork. I did made some changes with regard to the code, but again, not the code, but the contents of the layout of the code, just to make sure that you understand and how to apply to it. You see that in this case, the dash is always with regard to me. Okay. I need now to move to the next level, and the next level is that we are going to see, and when we apply the R, he will apply also the statistical result with regarding to hypothesis testing. And usually we are when we are doing that, we apply hypothesis testing. I hope you remember that from Introduction to Statistics. And in this presentation, I'm going to talk about null and alternative hypotheses. I'm going to talk about t-statistics. I'm going to talk about p-value. I'm going to talk about significant level. And hopefully I'm going to talk about one sample z-test and the power and the sample size, because one of the things that if you are using to determine the sample size, you will see that the package also use a power calculation in order for you to determine that. So I want to cover that module. So what do we have here? We have population, we have a sample, we have statistical interference, we have two forms of statistical interference with regard to hypothesis testing and estimation, as we talked about that in the last module. And we have the statistics and the population, and what does it mean with regard to the mean and the X hat. So I try to summarize everything into one table to make sure that you understand that, and how population versus a sample. The population usually is the idea of mu, and in the sample we usually talk about X bar, as we did before. And so what is it? What is a hypothesis? Hypothesis is a claim about something about the population. Example: the mean monthly cell phone bill in the city is mu equal 42. This is about the entire population. It's not about the sample. Or another example is the proportion of adults in this city use cell phone is, and I will give you the pi equals 0.68. Those two examples is talking about the entire city, not the sample that you're going to take from. In the hypothesis, we usually have two types of statement. One is a null statement, and one is alternative statement. The null statement, or the null x 0, is a claim or assertion to be tested. This is what we test. Example: it's also the average manufacturer board is 30. So in this case, mu is equal 30, and that's what we will test. And in this case, it's not about the sample, it's not about X hat, it's about the entire population. So we begin with assumption that the null hypothesis is true, and in this case, the notation is innocent until proven guilty. So in this case, it is the idea that it is always contain or smaller or bigger, and it may or may not be rejected. Alternative is what the outcome of testing the null hypothesis. So basically, we are going to state that the average dimmer of manufactured board is not equal 30, and the challenge the status quo. So we never contain smaller or bigger, and we might not even use it in order for us to test to see if it's true or not, because the main objective is to test the null hypothesis. So the claim that the mean average is 50, so the mu is equal 50, and the mu is not and the alternative hypothesis is not equal 50. So we will take a sample, we will test it, and we will try to understand what it means. So what is the procedures in hypothesis testing? So we are supposed that the mean average age is X, it's equal to 20. So this is significantly lower than the claim of the population age of 50. So if the null hypothesis is true, the probability of getting such different sample mean would be very small, so you will reject the null hypothesis. In other words, getting a sample mean of 20 is unlikely. If the population mean was 50, you can conclude that the population mean must not be 50. And again, this is the layout of the land with regard to the hypothesis process. We are starting the process with the null hypothesis is true, and when we able to reject that, it is where we are trying to prove that the sample prove otherwise. As we are talked about critical values beforehand, it is also about critical values in hypothesis testing. And so how far is far to reject the null hypothesis? This is again where the critical value of the test creates a line in the sand in order for us to make better decisions. And so again, this is where we are going to say too far away from the mean and or accepting or rejecting. In hypothesis testing, we also need, as we did beforehand, we also have the issue of error. There's two types of error: reject the true null hypothesis, or failure. The type 2 is failure to reject false null hypothesis. And it is considered to be a serious problem, and we try to manage it or try to outline it and show that the evidence will support that we are not taking the type 1 or type 2 error into account. So we need to prove that there is no error, or there is no error in probability, in order for us to reject or not reject the null hypothesis. So possibly error of how do we make the decision regard that is the ability, the confidence level of the hypothesis, and again we multiply it by 100% in order for us to do that. And with regard to rejecting the null hypothesis is the probability of H2 is false when we are doing the power of statistical test in order for us to verify that. I also need to talk about the relationship between type 1 and type 2 error. And there is no error cannot happen at the same time. It can be one or the other, and it cannot happen at the same time. So type 1 error can only occur when the null hypothesis is true, and type 2 error can occur when the null hypothesis is false. Again, the issue of that is really effective and really important in order for us to determine it, and there is always two-tail test in order for us to, there is a rejection region in both trails in order for us to prove that. We also have the idea of testing for the mean, and when we have the mu is known and when the mu is unknown. In the mu is known is called z test, and when the mu is unknown, it's called t-test. So I will highlight today only the QZ test because I feel that I'm covering too much, and I am myself as the presenter getting lost. I don't want that to happen. I'll go over it again next time, next module, but let's go over the Z score, the T-test. And the idea here is that the Z is equal to the X hat minus the mu divided by n square, and by doing that we are able to convert the X hat to part of the formula to calculate the Z score in order of the Z test in order to determine if it is acceptable or not. And there is a rule, decision rule, that if a test falls into the rejection error, otherwise we do not reject the null hypothesis, and that's a general rule. Two trails, again, this is where we have to test in order for us to show where the evidence lay out for us in order for us to determine the rejection. And there is a 6th step in hypothesis testing, and I'm going to read that as from the card, from my PowerPoint slide, and I want you to have that in your back of your mind because it will repeat itself. And especially when you are trying to write a report using hypothesis testing, this is part of the terminology that will be expected of you to write an accurate and precise report. You have to state, let's start with the first one, you have to state the null hypothesis and the alternative. 2, you have to choose the level of significance and the sample size. 3, you have to determine the appropriate test and the sample distribution. You have, number 4, you have to determine the critical value that divide the rejection or non-rejection region. And 6, collect the data and compute the value of the test. And 6, make the statistical decision and state the marginal conclusion if the test falls into the non-rejection region. Do not reject the null hypothesis. If the test falls into the rejection region, reject the null hypothesis. Express them in numerical values in order for you to have some context into the problem. Example, I'm stating that the null hypothesis, and I'm going to say specifically desired level of significance and the sample size. Suppose that the sample size is 0.05 and the sample size is 100. And so in this case, I'm going to state what does it entail, how to determine it, and this is identify null or alternative hypothesis. How do we write it with words with not only R? And the idea here is again how to apply it, how to determine it, see step by step in order for you to identify it and to reject or accept the null hypothesis. That's it. I hope you enjoy that. I will continue. I did not finish. I know it's a long module. I did not finish, and I hope that you enjoy that. I have the PowerPoint and more reference, more text reference to the subject. I hope you enjoy it. Please let me know if you have any questions. Until next time, have fun.